Hello, in this installment, we're going to talk about the small angle approximation. Simply stated, the small angle approximation is that for small angles theta, theta equals sine theta. So clearly that can't be true, that theta equals sine theta. But this small angle approximation is saying it's approximately true if the angle is small. So of course that begs the question, how small is small? Or, perhaps equally important, how large can theta be before it's no longer a valid approximation? So let's first, we're going to experiment to see how we could come up with such a relationship. And we have angles here. We'll explore 0 to 90. And we're going to convert the angle to radians. So we have a very precise value of pi over here. And we have radians degrees, the ratio of radians to degrees. So 2 pi radians is 360 degrees. The angle in radians, the ratio of the angle degrees, is a constant ratio. So solving for the angle in radians, cross multiply, we end up with 2 pi times the angle in degrees divided by 360. So we type in equals 2 times pi, which is 3.14159,265, times the angle in degrees, which is located in this column, divided by 360. And yes, we want to fill that down. We want to take the sine of that angle, equal sine of this angle. Now, how we could tell whether or not these were the same is by the difference. If they're the same, the difference is 0. So we'll make this column equal to the sine of the angle minus the angle, and we'll fill that down. So next, we'll take all of these and fill them all the way down to, let's say here. So 90 degrees. Now the sine of 90 is 1, so that's a good check. So we might notice now the numbers are really kind of messy. So what we're going to do is format them all and then bring them all over to one significant digit. So we can see that at one significant digit, they're not the same. But to one significant digit, when we get to 85, it looks like they are the same. Whoa! One significant digit, sine of theta does equal theta. Oh, 85 degrees, one significant digit. Well, let's change it to two significant digits. Now, that's to the nearest whole number, I should have said. It wasn't one significant digit, but to the nearest whole number, 85 degrees it holds. To one significant digit, we can see, we're getting close, 0.1, 0.1, a difference of 0. So at up to 38 degrees, one significant digit, they are indistinguishable from each other. And you may say, I noticed that they aren't the same, 0.7 and 0.6, but when we subtract the two, they are so close due to the rounding. You know, this might be 0.65 and this one might be 0.65 and this one might be 0.61. So they're rounding to the same. When you look at the difference, it's much less than 0.1. So at 38 degrees, you've got a difference of to one significant digit. Now let's try two significant digits. Now we get to two significant digits. It gets down to 17 degrees. Now in science, generally, we don't consider that we have a measurement until we have at least two significant digits. So this is really where it would come into play for us when we have two digits in our measurements. There's the certain and the estimated. So we're looking at here. So up to 17 degrees. And let's try now our three significant digits. Three significant digits to 8 degrees. And we, of course, should try four significant digits up to 3 degrees. 4 significant digits up to 3 degrees, and why not hit 5? And lo and behold, up to 1 degree. So the number of significant digits, 1, 2, 3, 4, 5. 5 significant digits were good to 1 degree. 4 significant digits were good to 3 degrees. 3 significant digits were good to 8 degrees. 2 significant digits were good to 17 degrees. And 1 significant digit, 38 degrees. So you might say, then, what's reasonable? Well, 2 significant digits, we've said before, is the minimum you would have for a scientific measurement, with 1 digit and 1 estimated digit. But up to 8 degrees, and you could see then the smaller the angle, the closer the approximation of theta equals sine theta is to reality. Now, for phenomena over which the angle is very small, 1 degree or 3 degrees, we get even more significant digits, 4 or 5 significant digits. And so it's very, very reasonable. We get very, very small. You might imagine then that we're measuring something infinitesimally small, like, for example, the parallax of a star moving, which we're measuring in terms of 1,000th of a degree. Well, now we're talking of lots of significant digits, and this approximation would be very good for something on that scale. In the next installment, we are going to look at cosine and tangent and ask ourselves, does it hold for cosine and tangent too? Stay tuned.